So probably we will start. Good morning, everybody. Welcome to our machine learning meetup. And today this meetup is special because it's under NeurIPS umbrella. And I hope you hear me all. My name is Elnaz Babayeva, and I am a researcher in Czech Republic in Innova Software. And this meetup, as I said, is special because it is part of global network of local NeurIPS meetup. As some of you know, that NeurIPS is the biggest conference in machine learning in the world. And this year, because of the Corona stuff, they tried to locally connect researchers from different places. And so I, with the great help of Marek Modrel from Machine Learning Meetup, organize this talk today, and also there is going to be on Friday. So today and on Friday, we will hear some talks who had accepted papers to NeurIPS this year or last year. And we will start with Alexander Shekhovtsov. He is assistant professor in CTU, and he will talk today about explainable training of binary neural network. So Alex, the floor is yours.
Okay, thanks, Eli. Hello, everybody. Let me start the presentation machinery. In just a second. So I need to turn on the screen sharing. It's a little bit weird with two displays. So you presented it is like so very much connected to NeurIPS, but I wanted to make a talk. You see it? I wanted to make a talk that is more kind of a little bit in a broader sense about my research and a little bit more accessible. So I will mention the NeurIPS work in this context. So it is in the same context, but just a little bit ahead. So also put in some new results and a little bit more about simpler things. So this is called explainable training of binary neural networks. And okay, I'm Alexander Shekhovtsov from Czech Technical University. And so this is the model that we will gonna discuss. We have some input here for the, let's say, classification problem. It would be an image. And in this model, we leave the first layer maybe convolutional or fully connected with real valued weights, because maybe the input is real valued and we don't want to lose all the information. But then once we apply this one first linear bank of filters, we binarize the activations to the range -1 to 1, so two values, only two binary values. And then we process it with sort of linear filters that only have also only binary weights, so -1, 1. And there could be like several layers like this. And then some output, maybe weighted combination, and a softmax classification model in the end, as usual. So such a model. So that's how one layer looks like. You don't see my mouse cursor, do you? Okay, never mind. So this is a kind of somewhat simplified model of what is practically proposed in the state of the art. But for the purpose of understanding the training mechanisms, we study this one. And so the main motivation behind using such models is computational efficiency. So this is very efficient on existing GPUs, CPUs, mobile devices. It's very efficient if you count energy that you need to implement elementary binary instructions. So in principle, if somebody wanted to put such models on FPGA or somewhere, that would be way more efficient than working with the floating point numbers. I don't know, we are talking on the GPU, we are talking about speed up of a factor 60 or so. Okay, and then there could be, in principle, other further use cases for binary activations. So, for example, if we train a binary descriptor for images, that would be very useful for quick search, quick retrieval of similar images. So there is this research done in this direction. It can be also useful for conditional computation. So you have a gating function that switch on or off some branch of the network. So depending on the input, you could use the different circuits to predict the output. That's very also interesting. But so far, not about this. So far about the problem. So how do we train such models, given that all this stuff is binary? And to look a little bit in detail, what happens in one neuron. So I've detailed here this specific component. So this would be the input, these three binary variables. So if I point with the mouse on this screen, you see the cursor? Okay, thanks. So this would be the input. Here it's binary, and we say the weights are also binary. And in principle, nothing prevents us from modeling the weights the same way that the binary inputs. So we will use a binary activation function and put in some dummy real-valued variable that we will call latent weight. So what we care only about is this, we're going to be positive or negative. So the sign of this latent weight. And then this goes into the multiplication and the summation. So as usual. And then we have this binary activation on top. Right. And the problem is, so we can kind of boil down, the problem is that how do we handle the training using the binary activations in this model? And so this is the problem. We have the activation that is given by sign of some pre-activation. And if you try to plainly compute the gradient of this for training with backpropagation, you get this. So everywhere you get 0, except at this point where the jump occurs, you get something depending on how you define what should be the gradient at that point. But that's obviously not really going to be useful for training. So what is done in practice is that instead of using this almost everywhere 0 function, you substitute it with the gradient of some other function. So, and there are really many different proposals that can be found in the literature. So one proposal is to do this. Don't consider the Jacobian of the sign function at all. So pretend that on the backward pass, you just, the sign function was identity, so that the gradient is passed with the coefficient 1. So pretend that sign was not just there and differentiate as if it was not there. There's some other proposals that, okay, so this is sometimes called clipping the gradients. Let's say on the backward pass, you will use the gradient of such function. That's called hard tangent in some libraries. So that means that it zeroes out the gradients that are too large in magnitude. Or we can use some other smooth proxy functions that will give us some kind of derivative to do the backpropagation. So this sounds like very empirical, like why would we do that? So what does it make sense? So at first when I saw this, I thought, okay, so this cannot be the right thing to do. But in fact, this works surprisingly well. And we will get a better understanding why in some moment. So, but the state of the art about this looks like this. So there are really many heuristics and obscurity in the field because there are these different possible ways and rules how you can propagate through the activations. there are also different rules. What would you do for the binary weights? You can use different fake gradients for weights and for the activations. There is this controversy or the problem that we said we can model the binary weights as the just binarization of some real valued parameters. But since these real valued parameters do not matter at all, so some research works say, okay, these latent weights do not exist. We need to do some optimization over the binary weights, some combinatorial optimization. And for these functions, for which functions to use to substitute the gradient, the reasoning is also half empirical. Okay, so they say here, if you use such function, doesn't matter how it is defined, the proximity to the original sign function in the term of this total area, total variation from the same function is better than for this function, and therefore it is more accurate, it's better for training. They showed better training test performance and test performance. But in fact, so this is arbitrary, right? You can make it by scaling this function, shrinking it, you can make it arbitrarily close to the same function. And you will get back just to the situation that this approximation is accurate, but the gradient is zero almost everywhere. Okay, so there are now, I have seen papers that are trying to study which of these approximations work better in which conditions. Also the papers that trying to study what the latent weights are doing during the training, how do they behave, so some statistics, how they change during the training. And this is, I think this is the very empirical, like a golden rush age. So all means are good to get some good results. But from the research perspective, to me, it looks like this. So there is not only the black box as the neural network itself, that is the predictor, it's also the training method is a black box that people trying to poke with different, to make experiments about the training method itself without the understanding what it should be doing. And I think this one really should not be there. So somehow I can accept that the neural networks are hard to explain the reasoning for predictions, but I think we should get a good understanding what the training is doing and advance it also a little bit by analysis, not only by probing. Okay, so now you understand my motivation for say an explainable training of binary neural networks. Okay, so one case for obscurity is when these straight-through estimators are introduced, it's always said, okay, we just pretend that the sign function is not there, so we transmit the gradient signal through the sign as it was identity. But then there is this subtle thing, is that what do you put under the sign function? So for example, I can put here in scaling such that this does not change the forward path of the network at all. So the sign is the same for any scaling that I put in here. But this changes this straight through gradient estimator, because if you say the gradient of the sign is identity, this scalar pops out in front of the derivative. That means basically you not only have the shape of this fake gradient estimator that affects the result, not only this, but also how you parameterize your model, how this, what do you put under the sign. So this causes lots of confusion. And in particular, many works, they are putting even the non-linearities in the sign, but non-linearities such as ReLU that, or leaky ReLU. So the leaky ReLU does not change the sign. So it should not have effect on the forward pass, but it affects the gradient estimate. So that makes it more obscure, and the total effect of these things is not clear. So this is a little bit my representation of the family of this straight-through estimator methods. So the tree of all the research that stemmed. I would say that there is a first mentioning by Hinton in one of his lectures. there was then a first paper that gave the name straight-through estimators and studied it empirically and made some alternative proposals. So studied it a little bit analytically, the alternatives. And then there was these seminal works that apply these sort of techniques to training networks with binary weights and the full binary networks with binary weights and binary activations. And from then on, there is really a plenty of methods, different innovations, residual connections, whatnot. Really many of them. So also I put here on the side that categorical and quantization also trained with similar straight-through estimators, but we don't touch them at the moment. Okay, and what is to note about is this first works. They were working on stochastic models. So the Hinton was speaking about stochastic autoencoders, where the binary codes were Bernoulli units, so they were random variables. And Benjo is speaking about stochastic neurons, where the neuron there was injected noise in the neuron. And then these two works that were kind of seminal for showing that you can train a deep network with the binary stuff. They were touching a little bit stochastic, so they were saying, okay, let's do randomized rounding, but they did not say why would they do this, or they did not say whether it is better or not, so there was nothing really about that. And the main body of the work that we see today, there's really many of these works, they using this deterministically as I've described earlier. So this has switched the paradigm a little bit in applying these methods. And I will go back to the stochastic model because it gives a sound way to understanding the straight-through estimators. So what is the stochastic binary network? We say in front of every binary operation, we add a noise like this. So with some known fixed distribution, like logistic noise, or we can put any other. And what is that? So if I have one binary activation and I add the noise before this binary activation, in the expectation of the output over these noises, we get a smooth function. So for one unit, it will be the cumulative density function, cumulative distribution function of the noise itself shifted depending on this input pre-activation. But now we do it for the complete network. We do it for the complete network, and we look at the expected output of the complete network. And so this way we get the stochastic relaxation of a binary network. So we're interested, what is the expected prediction of the network over all the noises? And this one is a smooth function of all the dependencies of all the parameters. So the gradient of this stochastic relaxation is well defined. So the gradient of the expected value of the function under the noises is well defined. We can compute it for some models exactly, for small models. The only thing we cannot do, we cannot switch this to the expectation over the noises and the derivative. So we cannot, once you put the derivative inside the expectation, we are back to the same problem. So if this realization of these noise variables are fixed, there is no more kind of smoothing effect from the expectation. We get the non-differentiable, we get zero gradients. So it just did that there is no mathematically correct way to switch these two operations, the gradient and the expectation. So you need to really look how to better approximate the gradient of the expected value of the function. Okay. So one more illustration example, what this stochastic model with injected noises can do. So suppose you have a training data like this, 2D features, two classes of points. So it's partially overlapping distributions. And this stochastic binary network, we say it's expectation over all the noises. If I fix the noise realization like this one, so I say all the noises I draw randomly once, and then I try to classify all the points in this plane. We get these decision boundaries that, so this corresponds to a single deterministic binary network, and it has this several linear decision boundaries combined. So it's okay, but it's limited representation power, we could say. If you fix the noise realization to some other particular value, we get a different binary, purely binary neural network that gives such a classification. So this total expectation over noises, this is sort of summing all the results of these binary predictive distributions to form the ensemble. So these noises, they can be considered also as, in some sense, useful, because they allow us to model an ensemble of binary network in one bucket, and they can be further useful later on if we are interested in seeing whether we get different predictions or the same predictions with the members of the ensemble to assess the uncertainty of the network. So, okay, so what we did, we started from this problem, how to approximate the gradient of the expected value of this function over the noises. We did some math here in this box that we took some exact steps, like, okay, you expand this, you can calculate part of these derivatives exactly, you can do some manipulations that do not introduce any error. And then we only needed then one approximation to make it a very simple computation. So the approximation that is there is that we need to linearize the loss function. Okay, so this speaks about one layer, but in the deeper models, we would also need to linearize more. I'll come back to this. So what does it mean we linearize the loss function? So if the loss function is a function of discrete variables, so binary plus minus one variables, so here this finite difference occurs. And this one is replaced by just kind of gradient of this function times the xi that gives the sign. And 2 is coming from that, the difference between these two, it's plus minus 1. So it's the total difference is of 2. And with this approach, we got this very simple algorithm that says the following. You need to, on the forward pass, you need to sample your binary variable. Okay, so that's identical to sample the noise and then to propagate through the binary activation, or we could say we take the noise cumulative distribution function and draw the output from this binary distribution and then convert it to the plus minus 1. And on the backward pass, so this is implied by these calculations. I do not need to invent what is the derivative through the sign. It's just that if we denote that the derivative of the sign would be equal to this, this allows to implement these calculations. So we kind of abusing the backpropagation to compute what we already know we want to compute. So the backward pass should do this. It should take the gradient of the noise cumulative distribution function and multiply it with the gradient from the downstream layers. So that's it. And that's actually, we then were quite surprised. We actually rediscovered exactly what the Hinton was proposed. So, and to show you that I'm not talking abstract things here. Right. Okay, I think I forgot to click. Damn it. Okay, this is gonna be a little bit bumpy. Yeah, I skipped this part in the sake of the time. I failed to connect the audio signal to this presentation. So I have here this video that is it's 10
so during
seconds.
The forward pass, we
during the forward pass, we stochastically pick a binary value using the output of the logistic.
And then during the backward
and then
pass,
during the backward pass, we pretend
transmitted
the
real value probability,
probability,
and that gives us a smooth gradient for back propagation.
And that gives us the smooth gradient for back propagation. So this, I was just wanted to show that it's really exactly matching to what we have derived now, up to this a little bit of dancing with this 2, because we used sign activations and not 0, 1. Anyway, so I'm putting this on because lots of body of this research here downstreams actually do not know about this stochastic definition of this straight-through estimator, and cites this works as if they were doing the deterministic straight-through, as is commonly done in the largest body of these works. Anyway, so Hinton has it before, so what we can add to this? We can add analysis. So now we have derivation, we understand where it comes from, because he proposed it like, okay, we use it as a heuristic. We don't know why, but it works. Now, so this was our motivation to write this work, reintroducing straight-through estimators. So they already exist, it turns out, but now we want to reintroduce them in the way that we derive them, and we give them together with the properties, together with the analysis, together with the understanding of limitations and some usage properties. So one property that we get immediately is that these transformations on the sign, if they applied like this, so if you apply the transformation to the proactivation and to the noise coherently, this does not change the estimator. So any monotone transformation will do, not only scaling. If you have the loss function is linear, we show that the estimator is exact. So we say it's random because it's drawing noises on the forward pass, but in this case, it does not depend on this noises. It's just 0 bias, 0 variance exact. If the loss is multilinear is like x1 times x2 and such terms. Still 0 bias, so it's random estimator, but it is estimating the correct gradient that we wanted. If you have quadratic loss, we can use the identity that for any variable x squared equals t1, and using this identity, we can remove all the quadratic terms that will convert the loss to multilinear. So we would know how to modify the loss such the estimator becomes 0 bias. Smooth loss. We give conditions for, we ask the question, so when is the estimator has the same, is aligned in direction with the true gradient in terms of the scalar product between them. So if the scalar product is positive, the optimization step in the negative direction of the gradient will improve the objective function that we want to minimize. So that's good. So if the positive scalar product is the true gradient, that's good. So we look at the conditions when the loss is smooth, when this is the case. So we can say something about the identity straight-through, is that this one that just pretends that sign is the identity. Also, sufficient conditions for a positive scalar product with the straight-through gradient. We can say something even about this deterministic straight-through estimator. What happens if we drop the noises on the forward pass? And we can draw some conclusions about when do we expect these estimators to improve. And one of them is that if you just put more units in this binary network. So this was proven by experiments. So we looked at this stochastic autoencoders. Sorry, I lost the track of the time. Can you help me with this?
You have, I think, around 10 more minutes, 8 to 10 more minutes.
Oh, okay, we are good. Right. So let's look at this stochastic autoencoder. And the model is to take an image or a text document or something and to encode it into very compact code, let's say 8 latent binary units, so 8 bits. And these 8 bits are Bernoulli, so they are randomized in this stochastic autoencoder. And we tested the exact gradient estimator that is now represented by this unbiased augment reinforced merge estimator, this one, and several variants of this straight-through estimator and the Gumbel softmax estimator. So what I wanted to show you here is this diagram, this cosine similarity for the 8 units we see. So this we measure during the training. So first, when we start random initialized network, the gradient estimator is aligned with the true gradient. So cosine similarity is positive. Good, we can proceed training. But then after some time, it gets negative. So it means that if we do the steps, it will actually increase the loss instead of decreasing it. And this is really what is observed here on the training loss. So this curve here starts growing. So that's the bias of this straight-through estimator. But once we increase the number of these latent units, increase the number of hidden variables, so this growth effect is not observed anymore. And this cosine similarity is kept positive all the way during the training. So some useful understanding like this. And then in the end also we have this phase here to correct our point with the unbiased estimator. And sometimes this gives a big jump from the current point to the, if you apply the unbiased estimator at the point trained by a biased estimator. So what's going on? How this is possible? So the illustration for this is something like that. So suppose this gray thing is the true landscape of the function that you want to minimize, the expected prediction of, so the expected loss of our stochastic network. And this, let's say this red dotted is some sort of approximation of this function that we get by using a biased estimator. And so the biased estimator, imagine that it estimates this approximation to the function instead of the true function. And in the beginning, it would be decreasing in terms of the loss of the true function and the approximation as well. But at some point, it might keep like decreasing the loss of the approximation, but the loss of the original function might start growing. So you see it goes here ascending in the level lines of the gray function. But it still goes somehow in the direction towards the optimum of the true function. So we are approaching closer to the direction of, to the point of the optimum of the true function. And this is why the unbiased estimator can very easily correct from this point to this point there. So this is what we observe here in this rapid jump. It doesn't mean that this unbiased estimator is so good in optimizing. If you apply it all the way from the beginning, it gets stuck somewhere here. It just means that it is good for correcting this accumulated bias of these biased estimators. So this is one property to take into account, that these estimators can accumulate an error. Right, so one more thing. So latent weights do exist. We prove this by 2 theorems. So we quite rigorously show that if you do common stochastic gradient descent in these latent weights, and you use the identity straight through. So what is the identity straight through? We don't have gradient from the noise cumulative distribution here. It's just pretending that, so it uses the identity Jacobian in this place. So we can rigorously show that this implements the mirror descent in the weight probabilities. So weight probabilities are continuous variables. You can pose the problem to optimize this stochastic binary network in continuous probabilities. So this is the essence of stochastic relaxation. You can so approach this problem. This is constraint problem. Probabilities must be from 0 to 1. You can approach this constraint problem by mirror descent optimization methods. And it turns out that this optimization can be written in the form of such a simple straight-through estimator on the latent weights. So this is why we now distinguish these two types. So straight-through activations. Here we cannot use the identity. The previous experiment showed that identity in this place doesn't work at all, and analytically it should not. But for the weights, it's a correct thing to do because it corresponds to the changing of the proximity metric for the steps. So it corresponds to the optimization adaptive method that you apply, you see? And by choosing the noise distribution here for the weights, you are choosing the metric that is used in this mirror descent. So mirror descent can be applied with different divergences. And here, the divergence corresponds one-to-one to the noise CDF, to the noise cumulative distribution function that we select. And furthermore, if you apply weight decay on these latent weights, you can regularly show that this implements variational Bayesian learning, if you know about this. Okay, so we tested this mirror descent approach, and we tested different noises in the activations. And we found out the following: all these noises that we put in there, if you do things consistently, so that means sample from this distribution on the forward pass, take derivative of this distribution, sample noises from this, take, use this as a derivative of the noise CDF on the backward pass. If you do this consistently, the results are almost the same. So we cannot say that there are statistically significant difference between them. So this doesn't matter. So it's a choice of model parameterization. It could affect, in principle, the training, but in this case, it does not. So it really did not matter much. And there is a clear improvement if you use sampling on the forward pass, if you do stochastic. If you compare it to deterministic training, there is a clear improvement from here to here. And there is a clear also improvement if at the test time we use multiple samples from this stochastic binary model. So if we use it in the ensemble mode. Okay, so I should also remark that in all cases for this training, we achieve 100% training accuracy in all cases. So basically the limiting factor why we cannot make it work better is the question of generalization. So we do not address the generalization in this work at all. We were caring only how to accurately estimate the gradients, right? So it's not the question here. So here everything is all right. If you know the tricks how to improve generalization by architecture or by some other data augmentation, I think it should be possible to improve performance. Okay, so next, if that is not enough, you could we have a more accurate gradient estimator. That's called this pass sample analytic gradient estimator. This is the NeurIPS work. It's more difficult, but in the end, it boils down to something computationally tractable. So somehow on fingers, what it does is that we do local expectations in once the other variables are sampled. So this one is summed explicitly. And then we encounter the difference of these probabilities. So what happens with the probability of this unit when this unit flips? And so such differences occur. And then we need to linearize these probabilities. There could be two levels how to linearize them. So we can either fully linearize them in the axes themselves. And this we will get the straight-through estimator in its deep form. So we will get back the straight through. If you linearize this difference only in terms of, so not in the difference of the axis, but in the difference of some elementary probabilities, we get still a tractable sim to compute that we call, that can be also implemented as a backpropagation, but this backpropagation should compute and apply different Jacobians for each layer that we call discrete Jacobians, and that results from approximating these differences. And we get computationally efficient procedures to that. So the total computation cost is same as for standard backpropagation, but is a little bit more difficult, method a little bit more difficult to implement, and some are constraints on the types of the models that can be handled. Okay, so we tested this in terms of the root mean squared error of the estimators. We take unbiased estimators. If you increase the number of samples, so the root mean square of unbiased estimator would decrease down to 0. So that means you can get as close as you like to the true gradient. But it really takes a lot of samples to get close enough. Whereas with this proposed method, if you take one sample, you already start here. So very small residual error. Okay, on this picture, so this yellow ellipse is the estimator that is unbiased, but with the high variance. So you get any point here inside randomly. And the blue picture is a biased but low variance estimator. So it might be more efficient overall to use the biased estimator, because if you have only few samples to try, one sample, you could be closer in the estimate to the true gradient. So this is what this picture shows, that this proposed past sample analytic method is closer to the true gradient for this very large computational budget number of samples. It's still biased, right? So it does not decrease all the way to 0. Okay, and so this we can test on the small networks. So if you increase the number of layers, so the variance of these unbiased estimators in the first layer, in the gradients of the first layer, it grows. So it grows, it becomes worse with the depths. With this pass sample analytic method, because it uses the passes, it also grows. So this purple stuff here, but it stays low it grows slower and it stays lower. Okay, something we can measure also about the cosine similarity between the true gradient and the estimator in terms of the samples. But what is more interesting is that if we compare this more accurate method and the straight through that I've described on the deep models, so this is 8 layers, all convolutional neural network, we see that they perform very similar. So in terms of this validation accuracy, they perform very similar. In terms of the training loss, they perform very similarly. So it shows that actually here, this bias, the accuracy of the estimator was not so much of a problem. So for these models, it seems that the straight through does the job. So there's no critical loss of the accuracy. So once we reach to the training loss very small, we get the training accuracy around 100%. That means that the accumulated bias did not spoil the optimization. So there's just no gain in this problem. But maybe if you encounter more difficult problems, so we have this more accurate method in the arsenal. Okay, I'm almost done. So this is the takeaway. So we put many different straight-through methods on the solid basis by explaining them using these different noise models, different noise cumulative distribution functions, and explaining the rules for the weights and rules for the activations differently. So for the weights, we could employ the mirror descent machinery. So this is why we have 2 different main estimators for activations and weights. So it works well with any noise distribution if that used consistently with the model. And in all cases, these resulting straight-through methods were strikingly simple. So I would say there is no wonder that they have been discovered first empirically, but I think we can still benefit a lot by rediscovering them and looking at their properties. So in the end, what we got is that understanding of the approximations that are involved, understanding of limitations, so when it gets wrong, and the ways to improve them if needed. So with that, I conclude and thank you, and I'll be happy to take questions.
Thank you, Alex, for your presentation. We have a couple of questions and not so much time, so we'll go through one by one. And I think a couple of them were answered at the end of your presentation. So the first one, you said that the binary neural network gives approximately 60 times speed up. So the question is it both during training and inference?
Test time. So we are speaking that at the training time, we need real valued gradients, we need real valued weights. It may be even a bit slower than the plain real valued networks. But in the end, we care about how fast it is when it is deployed in some devices.
Mm-hmm. Okay. The second one, how much worse precision of binary neural networks comparing to classical CNN? For example, you mentioned ImageNet or CIFAR.
Okay, yes. So there is a hot competition for the performance of this stuff on ImageNet. I think the top result is now is around 70% accuracy on ImageNet. That is using the residual network structure with two-phase training, with some distillation, with binary experts in between, with grouped convolutions, with a lot of stuffing.
So yeah. It's top 1, 70%.
Top 1, 70. Okay, you can see in the literature that it is been pushed further by further modifications, but the networks also become, let's say, more involved procedures, more complex things. Still computationally tractable, combining binary and real valued computations in some efficient ways.
Thank you. So the next question is, so you think your analysis can be extended to ternary logic encoded through one-hot encoded hard max?
Yeah, absolutely. I am looking at this. So ternary logic is easy. To get the ternary logic, you just need to take the sum of two binary convolutions. So this will give you the convolution with the ternary weights. Okay. If you have one hot hard max or one hot argmax, you need something like a categorical variant of this straight-through. So this is in the pipeline. There will be nothing very surprising in terms of the methods. I do not expect. So it will be something like on the forward pass, you sample from the softmax. On the backward pass, you take the Jacobian of the softmax.
Okay, thank you. And the last one, if BNN models have more parameters than classical DNN because of the binary weight, and the question probably how many parameters, the difference between the parameters.
I see. Yes, so the literature says that usually if you just keep the same number of weights, then the representation capability somehow is not enough. So often they increase the widths a little bit, but it's difficult. There is this issue that you need many during the training, but maybe in the end you can throw away many of them. So this is how these over-parameterized models work. It's the same for real valued networks. You need many during the training. It's hard to say, but typically you need in terms of number of weights, you need a bit more.
Okay. Thank you, Alex, for your presentation. We have slido.com, yes, for questions, so join us there. And also one more thing before I give floor to Vit, is that after the Vit presentation and the questions, we will have small networking at Geyser Town. When I check it out, it looked like Minecraft. So we can go to the world of Minecraft, go to the fake tables, to the fake scene, and like talk there. So for sure, go to check it out. It's fun. And now I wanna present to you Vit. Vit was a master student here at Czech Technical University, and now he's doing his PhD in University of Oxford. And today he will explain us and give us a bit of his glance at his research in generative art in and machine learning. Thank you, Vit.
Awesome, awesome. I have to click all the right buttons now. Right. Just checking, can everyone hear me so far? And can everyone see this screen?
We see the screen and
awesome,
we hear you.
Awesome, okay. Okay, so good morning, everyone. And thanks for joining the talk. I guess let's start with my part. I will be talking about art and machine learning, and sort of from two different standpoints. One is in art making, and one is in sort of research land. And the reason why I will be doing that is because I'm a PhD student at the University of Oxford, that's the research land, and then a TA or assistant lecturer at the University of the Arts in London. So that's my arts part, and sort of I'm trying to always connect these two worlds together. So I have some practical examples of when that happens, and also some general thoughts about the whole concept. So let's start. But before we get into these like exciting examples or application areas that I will be showing off, I guess we should go through some very basic concepts and do a really fast fly through these. Right. This is really basic, so probably everyone of the audience here sort of really knows this. So and it will be also very vastly simplified. So what's AI about? Well, it's about automation. What's machine learning? Well, it's about automation from data. This is vast simplification. You will see later as well that I will be simplifying other things as well, because I have to go through this fast. Cool. So what do we do with the data? We usually fit a model of some sorts, and a model is something like this, where basically we have some inputs, some outputs. These are two sort of domains that we feed into the thing in the middle, and the thing in the middle, the model has some sort of parameters where we sort of adjust some values, except it's more complicated. We don't have a single parameter, but many. Except it's even more complicated. So if we look at this metaphor of a model, we have a model which is sort of based on a biological neural unit, but it's not drastically simplified. And instead of using single neuron unit, of course, we have some very complex network which is doing some crazy smart things with the way how it's interconnected, or in what these different models are designed as. So yeah, we will not go into depth there, but we should get this sort of understanding at the start. When working with machine learning, we usually train this box in the middle, this model, with some training data. So that is the we train it on some like domain to domain sort of task on one set, and then we throw it out into the real world and see how it behaves with the real world data. And often this breaks because real world data is not as nice as the curated training sets that we trained it on before. But there is interesting things happening, right? Because we want to catch it and before it breaks, sort of, and see how well would the model generalize. Okay, so this is basically modeling some sort of relation between two domains. We have some input data and some output data, and this model is sort of trying to learn the translation between everything that we put here and everything that we put there. Andrei Karpaty has referred to this as a software 2.0. In the future, we will not have to write software of our own. Basically, we will be able to just throw in data at our machine learning model, and it will sort of figure out what's the relationship there. Right, so you might be wondering by now, how does this at all relate to art? And I will try to make that more clear later in the presentation as well. However, you can sort of imagine that if you throw in images at this concept, at this model, and these images are either representative of our own artworks or are in some way artworks from some data set, then this could become a tool that we can use to express something or do some cool tricks with this. Okay, what about art? Well, I think saying broad statements about AI is dangerous, and I think also saying broad statements about art is dangerous. So just keep in mind that this is just a simplification of both of these. I think art is sort of about communicating an idea or a concept, and it sort of can serve as a mirror to society. So if you look at some randomly selected pieces of modern art, we have something like the futurist dynamicism of a duck, where basically it's sort of a mirror to this fast style of living that we were getting even there, but obviously it's graduated even more now. We have abstract artworks, which are sort of getting away from realistic portrayals. So rather than showing some perfectly reconstructed reality, we would look at a reinterpreted reality in some way. And so these are the patterns by Frank Lloyd Wright, for example, or some other pieces of modern art, very abstract. This doesn't have to stick to just image-based data or artworks. Of course, you would have something like Waiting for Godot as a play by Samuel Beckett, which is sort of a mirror to the absurdity of life. Okay, so these are sort of the functions of art, although there is way more there. But yeah, let's just have this as a sort of general point. And now let's jump into the applications and examples, where I will be trying to bridge these two areas. And I think at every moment I will also try to say how these concepts that apply in art world could then eventually be used in something practical in the real world as well. Okay, so I broadly split the domains of art being made by machine learning into these 4 domains. I will just say at the start as well, and I will repeat it later as well, that this is very arbitrary. I think A, these categories sort of overlap. B, there are more categories. And yeah, but I had to do some sort of selection for this talk. So yeah, this is mine. Let's start with searching and representation. Then let's go to to explain some generative models. Then let's look at input optimization, and then finally the concept of domain-to-domain learning and what that can mean for like artworks or some research pipelines. Okay. So searching and representation by machine learning models. So this is roughly basically an area of representation learning in ML. So we would have this box standard, all the boring convolutional neural network. Probably you have seen this sort of diagram everywhere, where we have some images from some data set at the input side, and then at the output side we have some labels, some classifications. So this network has been trained to recognize that this is a car, this is a cat, this is a cat. Fine. If you look at the network, what we care about in this area of searching and representation learning is the feature representation. So somewhere in the middle of the network, we sort of have a cut, get all the values, and then work with them. So in this toy example, we have features that have the size of 2. So as this is a 2D vector, we can basically plot it on a graph or on a plane like this, and it's easy to see. But imagine that in a real world model, this would be many dimensional, not just 2. Well, what happens is that because the model has to learn that the cats are the same category, it sort of places them very near each other in this latent space. So we have a cat 1 here, cat 2 here, and if there is some other object, it would be probably positioned somewhere very far from these 2 similar categories. Okay, so what this is used for? Well, you probably know Google image search. I think roughly behind there is something like this happening as well, because we have this encoded query image, and then we can just look at the other images in the encoded space, in the latent space, which are nearby. Fine, this is easy task. We can also look at some sort of path between two images. So if we have encoded image 1 here and then image 2 here, we can sort of go in between these 2 points into space, many-dimensional space, and then look at everything that's nearby it, and then maybe collect all of these nearby samples and then show them. Again, this is in 2D. It's simplified. In many D, it would be more complicated. But anyway, and what I was just describing is exactly what was demonstrated at the X degrees of separation piece by Mario Klingemann, where exactly what I was describing is happening. We have encoded 2 images, these 2 images, and we are sort of looking at the path between them. Well, so it's possible to sort of look at the trajectory through the latent space between the realistic painting Tower of Babel and the modernist painting by Piet Mondriani, right? And so what's happening here is that we have sampled from a data set of paintings, artworks. So we had to have that data set, right, as well, before working with this model. But what this allows us to do is sort of look at some visual similarity between images and then cluster them together by this, or do a trajectory or like exploration of the space between 2 samples. So you can imagine that somewhere there would be a cluster of all the abstract paintings and cluster of all the realistic paintings, and it might be interesting to just go between these, or go between styles and see what's happening there. One caveat there is that this is looking at purely at the visual similarity. So maybe we would like to have some more information encoded there, some meta information of like the dates of creation, the authors and stuff there. But even without this, I think it could be a possible other approach to curating artworks, right? So you could see this in an art gallery, a mess of selection of sort of like progression of artworks through time. Well, which could be really exciting for the curatorial museum people that I know some of. Okay, cool. So let's go further. This is just a single example. This is referring to the search engine I was sort of describing before. So looking at nearby images, there is this project called TerraPattern, where, oh, okay. I don't know if your guys are also seeing this thing. Yeah, I'll hide it. TerraPattern, which is a work where basically they trained very similar models on images from Google Earth, and then looked at these patches, and then sort of you can just search by some query image and then search for everything that's similar. So you can have a collection of all the roundabouts in these states or whatever. This is Manhattan, but there are different data sets in Pittsburgh probably as well. I think this was, and so this is actually getting similar to some conceptual gathering of similar patterns and shapes that can create some new preview. And so this is from 2016. This is an automated algorithm, but in the in 2009 to 11, Jenny Odell was actually working on something similar, where she was going through Google Earth maps and sort of finding patterns that of one type and sort of collecting them and then displaying them in these plots of everything there being next to each other. And we get some idea of like, okay, this is a collection of one type of thing. But she did the same with like circular farms and some other, I don't know, factories and all of these objects. And her work has been displayed then on a Google data storage facility, which is quite fun because it was coming from these facilities, the data that she processed, found some samples, and then put them back there. But all of this has been done manually, and there are these techniques that can do it sort of automatically or help with that. Okay, well, until now it was just the beginning. We talked about the searching and representation learning. Sorry, let's jump into the second category, the generative models. And by the way, I'm sort of describing the categories here. This was the first one, and then we are in the second one, and then we will go to the third and fourth. There are many types of generative models, and sort of just to not overwhelm you, I will start with one which is called the generative adversarial network, which is this sort of outline. And we don't really care about what's happening, how it's being trained. We care about this bit, which gives us the capabilities to throw in some random numbers and then reconstruct or generate an image, which then will be something similar to a data set that we have trained it on. Well, so there has been a lot of advancement in this field of GANs. One quite large paper from a few years ago was the progressive GAN, and then a follow-up paper called Style GAN by the same author in 2018, which has been showcasing the performance of these models on human faces. And it's actually quite a tricky data set. I mean, it's easy data set in the sense that there are a lot of things that are same for all images of human faces, but it's a tricky data set because I think we as human beings are sort of programmed to be really good detectors at figuring out if that face is okay or if there is something wrong with that. So for them to actually achieve quite high fidelity there is quite nice. And so this paper itself also was pretty huge because it inspired a lot of other creative works in this field. So because you don't have to just train it on boring faces, you can train it on other types of data. So there were people working with aerial images and sort of generating aerial imagery data, but also trying to figure out how to tile them together. So create large maps, which are sort of in theory infinite. And that would be the tile GAN here. Or you could work with some fun data sets, right? So there is this project by Derek Schultz where the data set comes from the wildflowers of the world. And so you are generating some illustrations, and then you can sort of go through the latent space and then see how the illustrations are changing, creating maybe new patterns that were sort of not there before, or somewhere in the middle of the samples that it saw. And you can see some really like messed up shapes as well if you play around with the models, mess around with the models. And so why this would be useful at all is that this can be an inspiration of some pattern that we can later use. I don't know, I would wear this as a design on my t-shirt, for example, or we could go like onwards, and it doesn't have to be as simple as figuring out designs, but it could be an inspiration for something, some pattern making later. So I'm also interested in this bit, which is sort of feeding these generative models some videos, which is actually just a video of a single shot of some video footage, some similar scene which is repeating, for example, and then treating this film not as a regular film, which is time-based, where basically every frame has a time stamp, and then you are going time-wise from the start to the end. You can also have this generative model learn on it or train on it, and then you can go through this space in some way which is more similar to the stuff we saw before. So similarity-based sort of parsing through a space. And so this eventually gets into the area of experimental short films that you could see. And there is many more as well, which just doesn't fit here. So yeah. Cool. I think you probably might have heard about the GANs, and probably quite a lot of you already also know how to use them, how to train them, how to that is difficult, etc., etc. And so it's relatively boring to see those images I was showing before. However, there are some new concepts with GANs, which is sort of the area of inverting GANs, which there are many ways how to do it, but let's just simplify it by saying that instead of having a generator and a discriminator, we would also have an encoder, which is sort of returning whatever this generated image was back into the latent representation. And so you might have some losses there, and you might have many additional tricks. There are different types of doing this, and it's sort of in the area of current research, and I am sort of going through these papers, and it's mad often, but that's okay. And this concept then allows us to go from reality, encode it into the latent representation by using that trained encoder, and then reconstruct it by the generator into a reconstruction of sorts. And so this is something that you probably also know from autoencoders, which is actually a relatively old concept. But what it allows us with GANs is that they tend to have much higher fidelity of images, much sharper images, because of the types of losses they are using. They are not using or not comparing just the pixel values of the images and using some L2 loss. They are comparing some adversarial losses or forcing the model to generate in some other way that it makes sense. Cool. Well, so what can we do with these inverting GANs is that we could train it on our data set and then sort of play around with that. What does it mean is that we could then sort of interact with the latent representation of the image and do some edits to it in order to make some changes of the reality that we encoded. And so there were some papers which were working on some actually quite local targeted edits of some image, and you could sort of change it in the latent space, move it in some direction, maybe add a smile to an embedded image of face, and play around with some attributes like that. You can also mess around with the networks themselves. So the encoder and the generator networks are trained once, but then you can sort of play around with the weights and then change them and see what that does to your reconstructed reality. And so that slightly goes into the concept of going away from realistic representation of reality into some sort of abstraction, right? So that becomes more artistically interesting. Okay, well, not to end with art, this is also this whole concept can be also used in many examples for real world problems. So there is one that I found from 2020 using similar models like this for anomaly detection. So you have this model trained on how regular wheels would look like. You can input any currently made wheel or this item that you are making, and you can reconstruct it. And the way what happens here is that it sort of smooths out the errors and sort of reconstructs the image as it would be from the original dataset. And so if you then compare these two images, you can use it as an anomaly detection and say, hey, okay, there was something wrong with the wheel at this point, probably. Okay, and there are many other uses in this area for this sort of setup as well. Anything that you could use autoencoders for, you in theory could use these for as well. Okay, right, we are jumping to the next category, which is deep dreaming. I think this technique is relatively well known because it's relatively old, and also it made news, I think. and I'm saying relatively old, it's just 5 years, but in machine learning world, that is a lot. So how does this work is that we have an image that's on the input and the same old boring convolutional neural network that we were working with before, and which identifies the image that we placed in. But instead of using this as a feature representation or something, looking at the vector in some depth, we select a single feature and then we sort of iteratively change the original image in a way that it will maximize the activation of that particular feature. So this technique was originally used to actually just visualize what these features have learned, because in theory, you are selecting this one particular feature and asking it, okay, what type of image would this feature fire on the strongest? And so that was a tool of inspection of neural networks. But then in turn, it also just makes these very weird, bizarre images, which this has been used on the pointillist painting here and sort of reconstructed in or changed into different into showing different features enlarged. And this is quite funny because the pointillist painting was sort of going away from realistic portrayal and then using just points to reconstruct something. So if you go really close to this painting in a gallery somewhere, you would see points rather than the image. And only if you go back from this image, then it sort of blurs into this realistic portrayal. And so we are sort of doing the same thing, but with neural networks, which are replacing the dots into some different types of features that are reconstructing the original image. Okay, well, so we have reached the last category, and I quite like this one. It's the domain-to-domain transfer. I think it's generally interesting concept, and I think it can be used in many areas. And yeah, I will just explain why. So we are working with a model here, which is basically which gets some images thrown in from first domain and then some images thrown in from the second domain. And in some of these models, they have to be paired, so you have to have sort of exact translation between this image, and then you just create these data sets and feed them in. In some other papers, you wouldn't even have to have these pairs. It can work with any sort of data. But yeah, let's not go into the details too much. So what I'm showing here is the Pix2Pix paper. Again, it's relatively old now, which is image-to-image translation, where basically we feed in, we have trained these models on this sort of input, and then we are reconstructing this sort of input. So what this model is learning is that we can the translation between these two domains. So it sort of learns how to translate from semantic segmentations into real world images, or from black and white images into color, or from simple edges into some real world, real like images, or the translation that can be learned there could also be the change between day to night, sort of. And so you can of course see that in most of these cases there is not one correct answer, and so we can say that these results are sort of arbitrary. There could be many more outputs that would actually comply with the same input. Well, so this was in 2016. There has been some following work for this, and one of the ones I would like to mention here is the pixel to style to pixel, which is a relatively new paper from 2020, which is doing quite something actually quite complicated, but in the end we sort of can also just train it on the domain to domain. So I will not go into too many details about like how they used it. However, they are also able to sort of train the translation task from let's say semantic labels into possible real images, or from low resolution into super resolution or high resolution variants. And you can see that you can generate basically many possible interpretations of this low resolution image, or something like frontalization. And so why am I even mentioning it? Is that this paper is using some high resolution style gun generator, which then just makes it possible for these results to be actually quite high resolution and high fidelity of results. So you look here, this is very low resolution and like somewhat uncanny at some moments, but in 4 years of research, we are getting images which are quite real in the end. Right, so these are some techniques. What can this be used for? Well, this can be used for some fun stuff. For example, this pix-to-pix model was there are many types of these models, but like this one was trained on the edges to cats data set. So how they trained it was that they had a data set of cats, they generated these edges with some relatively simple algorithms, and they trained the backwards operation, so to go from the edges back to cats. And they released this model to the internet, and of course what happens is that people will throw in inputs that make no sense for it, right? But as a result, people can generate these red cats as a, for example. And so this is quite funny because this is showing the difference between the training world and then the real world issue, where this is nothing that this model has seen in its own training dataset, right? So somewhat similar to the cats images I was just showing is the artwork by Memo Akten, which is called Learning to See. And this is a piece that has been exhibited in an art gallery in the Barbican in London. And what this is doing is something similar to the previous slide, where we have also just a trained model from which is transferred, I think, from domain to domain. And it's looking at images of some old boring stuff that we just throw in before the camera. So some wires and some whatever here, basically. And then in real time, it's generating patterns of flowers. And it's basically going through the same as we saw before. So it's going through a stage where it just converts this into edges, and then also then reconstruct from edges back to flowers. And so the artistic statement there by Memo is the neural network looks out onto the world and tries to make sense what it is seeing, but it can only see through the filter of what it already knows. So that's the artistic statement. The practical side of it is it's a pix-to-pix model trained on edges to real sort of translation run in real time with some tricks in there. So let's look at the video here, because I think this comes alive the best when you can just see the video of it. So what we have is just some sort of like inputs that are on this side. It's being converted into the edges and then reconstructed as some different type of domain. And so the fun part is that it's running in real time, and you can sort of really play around with it and see what it does, what changes, and you can swap different weights, etc. And so, yeah, I quite like this work, even though it's slightly older now. Okay, let's get back then. So somewhat similar to the previous one, and you can see that I like domain-to-domain transfer, is the work by Anna Redler, Fall of the House of Usher with Pix2Pix. And this is, her works are quite usually using some model with her own created data. So what she made, what she has done with this is that she have painted her own sort of frames for a film and then trained a model on this to convert real film into this into this style of her painting, and then she has done this for the whole film with even the frames that she didn't paint on her own. And so she can then reconstruct the whole film by using the style that she made her own, sort of by painstakingly painting every frame. And so what we get is that there are some shapes that make some sense, but also don't, and there is we can sort of recognize what's happening there, but sometimes we cannot really. And we can get this sort of neural aesthetic as well, because there is some blurriness there, and there's some uncanny like things happening, and you can just sort of see squares, which is sort of because there are some convolutions operations happening probably in the pipeline, etc. And you can see interpolations between some like real shapes into weird samples. Well, so I quite like her work because she's always working with, or she's always interrogating how to sort of how to be artistic with these models. So how to bring in her own art into this, rather than just using the models as they are. Cool. So let's go into some more examples. This is one where this domain-to-domain transfer is used for a useful task. So the task is localization. And let's say that we are working with a huge pipeline where later in the model, we can recognize from images, daylight images, where we are in the city. That's the task of localization. But for example, if we want to extend this capability into night images, we could just pre-process these images with this 2-day GAN, which is converting the night images into the day-styled images, and then we can feed it into the other already trained networks. And so something similar has been done where you could be converting something like thermal camera footage into a visual-like footage, and then using that later in your pipeline. And so these are sort of really augmenting the sensor capabilities of what we are of what we had from the dataset. The problem there is that maybe if this translation makes no sense, then it will break the whole chain of the pipeline. But that's sort of for us to explore. Okay, cool. The last example in this category is the bit-to-bit sample. So let's look at just short preview of this, where they have the same domain-to-domain transfer task, but it's also running on a video. So we have some temporal consistency between the frames. So you don't see that much flickering from one frame to another. So that's sort of the trick of this paper. Cool. We are nearing the end of the presentation. So I will sort of just go stand further away from the exact, for the particular applications and look at some general concepts. Cool. So we spoke about art being a mirror to reality, sort of. So I'm also a photographer, so I like this parallel into photography. If you have a camera, you are sort of taking a picture, and somewhere from reality, you have chosen the frame that you want. You have selected the part of reality that you want, and you are sort of storing it into the latent film, into the latent form on your film. If you have a film camera, or as your digital file, which has high dynamic range data, if you have some other digital camera. And then in the darkroom or in your Photoshop room, whatever, you're developing from that form into one presentational image that you will then look at and use. And so the question there was really like, sure, but photography is bound to represent reality. How do we make any abstract art with it? Well, that was the question at the start of photography, but of course this was solved. And there were people talking that saying that, hey, photography is not art, actually. It's just reconstructing something. How can that be art? Well, so I sort of take I'm quite interested in using neural networks as a sort of tool here, which is able to somehow encode reality, the stuff that we are showing it, the training set, and then represent it in its own latent space, so in its weights basically. And then when we are playing with it, or when I'm using it to generate something, we are developing single frames from that space. And so I think in theory, these two could be sort of connected. And at the beginnings of photography, there were shouts that, oh my God, painting is dead, portrait making is dead, because we have photography now. And like, it changed the whole medium of paintings and also photography, this relation between these two, because you could say that it sort of freed paintings from realistic portrayal, and also because it has to sort of show in a way that it doesn't just represent reality, but photography. They had to come up with techniques like reality-less photography, so something like shining on a photographic paper in your darkroom on your own and sort of creating some abstract shapes there. And I think this could be sort of happening here with neural networks as well, that it would sort of move the mediums further and yeah. Cool. So how I see machine learning, I see it as a sort of co-creative tool that we can use when creating art. So I don't think that some sort of generative AI is an artist on its own. I think we, the authors or the programmers or people who are playing around with it, are the artists there. Cool. And finally, I also think that the machine learning and art can sort of be useful for each other. So new research can influence new artworks being made, and new artworks being made and displaying some concept can be used to inspire us for more research in machine learning. Okay, so to bring it to the end now, we talked about these 4 categories: searching, generating new imagery, deep dreaming some images, so changing the input. And I think that one is interesting because it's doing something different than the other fields. That's also why I left it there. And then finally, my quite favorite, the domain-to-domain transfer, where we can do something weird there. You might be asking what else sort of didn't make it to this presentation. I will tell you tons of it didn't make it in because we just have limited time. So something like interactive systems, where we have a generative model and we are sort of interacting with it in some way. And we see the results immediately, and we can sort of move around in the latent space in some way, which is sort of, it's different than just generating something in batch before. Something like using creative pipelines, where the generative model of any sort, any of these, is just a part of other models, and it can you can break the first one and see how everything else breaks. Or in research pipelines, as I was showing in the night to day gun presentation or example. And something like audio-visual generation, so in general just multimodal data. And if you care about this category a lot more, there are some examples in the current version of the NeurIPS creativity and design, machine learning for creativity and design workshop, and something like editing neural network weights directly to make them do some effects. Cool. So if you are interested in more of this, check out this NeurIPS 2020 creativity page. This is the workshop that I'm sort of linking this presentation to. And finally, thanks a lot for your attention. I hope it was not completely boring. I also hope I didn't go too much over time. And if there are any questions, I will be happy to answer them. Okay.
Thank you a lot, Vit. To tell the truth, I'm a big fan of machine learning and art, because for me, it's like, okay, I can do kind of machine learning, but for me to do art is something unbelievably cool. So there are a couple of questions, and the first one is about fake news and fake content. Mm-hmm. So we all know that GANs generate a lot of fake content. Do you think that it will be possible to get GAN-generated picture or video?
Yeah, absolutely. So it's like an arms race, right? You are even in the GAN layout, you're training generator to make as realistic images as possible, and the discriminator to detect these synthesized images. So even there, this arms race is there already. In real research, also you would have some papers that are sort of just trying to look at different types of manipulations with images and then trying to detect them. So not just generated images, but also just faked in your old Photoshop, just moving around things and like seeing that some pixels suddenly don't really work. Something we wouldn't notice, but an algorithm might. So yes.
That's good. If the artist, as you said, use machine learning model, who should take credit for the work? Artist, the model, or author of the model?
Yeah. So yeah, of course, that's a tricky one. I think there are sort of many ways of using these models, and I think there are only in some cases you are able to put in your own creativity in that. I think if you just download something from the internet and play it, it's not actually art. If you just train a network on a data set of images, I think that people from the art world are sort of tired of this because it has been done as well. So I think it will not be considered art either. But you have to do something crazy with it, or like something interesting, or something placing your own creativity into that. So there are multiple points where you can put in your curation. So you can curate the data set you are showing it. You can curate the selection of the models. You can somehow interact with, like, change the way how you are interacting with the model. So maybe your shown images are representing some trajectory that you found or something, and then you want to make some statement with what you are showing as well. Yeah, I think all of this is important. So and I think when all of this sort of happens, or at least some of it happens, the author of the artwork is the one who made this effort and who figured out this more complicated concept than just playing around with something and just showing the raw outputs.
Okay, so we can say that model is just like paint.
It's a tool, yeah. It's a smart camera, I guess, but weird one, yeah.
Okay, thank you. What are the ideas that you want to convey in these artworks apart from experimenting on new medium or tool? On a new medium or tool?
Yeah. Yeah, I guess it depends on the artwork, right? If you remember the one by Memo, the learning to see, I think the concept there was to show the idea that we are biased by our own, what we have seen. I mean, he has reached this by some tricks, right? Because technically it's not the same thing, but still the philosophical idea is conveyed there, I think. I guess you can influence that a lot by the data you choose. Yeah. So it is a mirror to society. So the mirror can be critical. You can choose something that you sort of care about a lot, about some conflicting statement. It's sort of like filmmaking in theory as well, because you could be feeding it images from film and then showing those images. It's sort of like weird way of cutting then, because it's sort of just flowing through some similar images, but you can employ probably more by post-processing the stuff that you generated. So it really depends from artwork to artwork. But check the what was the name of it? The workshop that I was talking about, the NeurIPS 2020 creativity, because there is quite deep concepts behind a lot of the projects that they show. Okay, cool.
Okay, and the next one is, when do we see the first gun-generated movie? It's what
I'm working on it. I maybe there's been something like done with this. I have seen like often these things will be explained by some demo on YouTube or something. So that also is already like a generated movie. But I'm not sure if there was a film made by these directly. Yeah, but there were many things like people generated not lyrics but text for a drama, and then they played it on stage, sort of using generative text, but then played it out in the real world. So maybe that could be also a generated movie. I don't think guns were used there, but it maybe doesn't matter which model you use.
Okay, and the last question: what was generated in the video-to-video?
Yeah, the example I was showing. Yeah, so I don't remember exactly. There were many papers I was going through here, but I think they were training on maybe two types of data sets. One was semantic labels into real-world imagery, and the data set they used, I think, is called cityscapes. So if you look, cityscapes is basically just video footage from driving through some German cities, and then you get this cityscapes imagery, and then you can train the models with this. And they were showing also the capability of editing the semantic map, so just sort of erasing all the trees, and what happens then is interesting.
Okay, thank you, Vit, a lot.
Cool.
So let me remind you that there is going to be also the second meetup on Fridays, the same time. The time was chosen that it's not overlap with official NeurIPS, so that people who attend the NeurIPS also can attend our meetups. So join us on Friday, and you'll hear a talk by Niklas. He is a researcher in CTU ASE. And also there's going to be 4 companies talking about their industry application and collaboration with academia on some topics. And now I would like all to invite you to the Geyser Town. I think it's fun. Yeah, and let's try it out and see how it's going to work like. It's like to be in Minecraft. It's super interesting. So I think it can be generated. We can generate much more rooms than with GANs, which Vít was talking about. So it's not the end. And actually, a lot of conferences use it for SB and networking, like to try it out, that we are closer to each other than just to our monitors. And thanks again a lot to Alex, to Vít, and also to Marek for organizing this event today.
Thank you. I'm gonna try in the Minecraft just at least to see what is this technology allows.
Does it work for you guys? I'm ending on the short URL page. I don't know, maybe it needs to be.
Sorry, just give me one small second.
Okay.
It seems that.
Okay, I'll take a.
No, the link that you posted in chat just takes me to the homepage of short URL.
It seems it expired. I will have a different link for you in 20 seconds. So, shooting a new link to the chat here.
Mm-hmm.
Okay.
And please don't forget to mute or sign off from Zoom before you join together, so that we don't get echo.